We've been talking about magnetic fields produced by electric currents, and we talked about magnetic fields due to current loops. And so we want to extend our discussion to magnetism in matter. Now, electric fields turn out to be far stronger than magnetic fields in the grand scheme of things. But magnetic fields hold a special place. Uh, Kids play with magnets. You don't normally play with electric charges. You have static electricity. I mean, a lot of people, I guess you do play with electric charges because you drag your feet on the ground in dry weather conditions and get yourself electrically charged and go shock somebody. That be an example, I suppose, of playing electric charge. But far more people play with magnets. Magnets, you normally, static electricity is like this annoying thing that you have with socks in the dryer. But magnets you use all the time to hold things to one another. Magnetic latches, magnetic refrigerator magnets, little things that you stick here and there, magnets, with advertising on them. So magnets have a special place for us, even though the fields are actually much weaker than the electric fields. Now, one of the reasons here is that with magnets, you can actually have a sustained magnetic field, whereas with electric fields, you get the electric fields, capacitor will hold a charge for a very long time, but really the charges are just aching to cancel each other out. And so the positive and negative charges will eventually, if they can move around, the electrons are very easy to move, they'll eventually leak out and neutralize charges. So magnetism, you have permanent magnets, which really aren't permanent, they just are magnetic for a very long time. But the other thing is that Earth itself is magnetic. So the planet Earth here acts like it has a giant magnet in it. And so we have the magnetic field here. Okay, and we talked about the magnetic field of Earth in a previous lecture and how the north and south geomagnetic poles are reversed from the actual magnetic north and magnetic south. So just pointing that out, reminding you from a previous lecture. The question is, how do we get a magnetic field in Earth? Well, we know how to get magnetic fields, this magnetic dipole. How do you do that? We have electric current going around. Well, how do you do that? Well, it turns out inside the Earth, we have a solid core, we have an outer core, we have a mantle and a crust. The outer core is liquid and is liquid metallic. So as it's moving around, turbulence in here can actually cause electric charge. Rotation of the Earth keeps the electric charge going around, and that will produce a magnetic field. And so turbulence shifts that electric charge around a little bit. The magnetic field drifts a little bit around. Compasses don't always point in exactly the same direction. They shift a little bit over time. It's called magnetic declination. You can measure that. U.S. Geological Survey keeps track of this and lets you know how far left or right of north a compass actually points at different locations on Earth. So this is our experience of magnetism that's with us all the time. And we know that these magnetic fields then exert forces on other magnetic dipoles. So if you have a little bar of metal, if one end of it is facing towards the north, the other end is facing towards the south, we call that end north, that end south. And so what's happening is that you've got a magnetic field in here. Okay, so you get this magnetic field that goes from the north to the south. Okay, and so magnetic field. All right, so there's your magnetic field. Okay, now inside, as these magnetic fields got to be closed loops. So, but anyway, so what's happening here is that we've got a bar magnet. So the question is, well, what makes it do that? Because we know that you got to have moving electric charge in order to make a magnetic field. So there's got to be moving electric charge in here. And the answer is yes, there is. There's moving electric charge in there. So what makes up a permanent magnet like this? Well, what makes up a magnet like this is matter. Matter generically is going to be atoms. Atoms have protons, they have electrons. They have neutrons too, but we don't care about them, in this context because they have no charge, so they don't do much. The electrons are on the outer part of the atom, and electrons act very much like they're going around like this. Okay, so around the nucleus. And so the electrons act like that. They don't really. We know for a fact that electrons do not really run around like little planets orbiting. We pretend they do because the math works out really easy, and it actually comes out pretty darn close to the actual values. And so, but it's really a lot more complicated than that at the subatomic level. That is a topic for quantum physics, which is beyond the level of this class. So we can't really get into that just yet. But we can say, hey, this acts like a little magnetic current loop. And so that is going to produce an electric field. And so the electric field, rather a magnetic field, and so the magnetic field is going to be a magnetic dipole of some sort. Okay, so there we have it. Now, we already derived the Bohr model and the Bohr magneton earlier in the semester. We had said that we know that the magnetic moment is NIA, so we're only talking about one current loop right here. And so I is going to be the charge per time. The time is the orbit. A is pi r squared, where r is the Bohr magneton. And then so we kind of worked all this out and said, well, we can actually multiply and divide by 2. So we have E 2 pi r over t divided by 2 over here times r. And so what we have here is the velocity. So this is E over 2 r times v. Okay, if we multiply by m, okay, and then divide by m, so we multiply and divide by m, then what we have here is mrv is the angular momentum. So this is going to be equal to E over 2m angular momentum. So that is the mu. Okay. And so the next thing that we realized is that the angular momentum can only come in certain varieties. Okay. So the angular momentum can only be quantized. So the angular momentum here is going to be equal to some number times h bar. H bar is h over 2 pi, where h is the Planck constant. We'll get back to the Planck constant later. Planck constant is 6.63 times 10 to the minus 34 joule seconds. Okay, so that turns out to be something we'll be using much later on in the semester. But we'll see where it comes in later too, because it comes in from the speed of light. All right, so there we have it. ML is an integer. It can be 0, or it can be plus or minus 1, or plus or minus 2, or plus or minus 3, or plus or minus 4, etc. Okay. So this gives us this angular momentum possibilities right here. And so that's kind of what's going on inside of the that's kind of what's going on deep inside of the atom. Now, if you have a whole bunch of atoms here, and the electrons are all going around in the same direction, then they're all making magnetic fields like this. Now, if the electrons, are all going around different directions, then the magnetic fields would all cancel each other out. Okay, so if they all go around different directions here, magnetic fields would tend to cancel each other out. So a magnetic domain in which you make them all go in the same direction amplifies the magnetic field. Now, this should sound familiar to you as well, because we've talked about this with dielectrics. With a dielectric, if you apply an external electric field, then you make a whole bunch of little dipoles. They all line up and amplify the effect of the field. And so, or actually, what they do is they tend to line up in such a way that they lessen the field right there, and so they would amplify capacitance and so forth. So here we have another example, and this is going to be related to what we call diamagnetism. If you have a diamagnet, then if you apply a magnetic field to an object that's diamagnet, then what's going to happen is it's going to end up inducing magnetic moment in there. That magnetic moment is actually going to be opposed in direction to this. Now, what would happen is that means it tends to repel. And so if you have a diamagnet, then, and pretty much anything that's made of matter is diamagnetic, then it's going to have a slight repulsion from magnetic fields. You apply a magnetic field and things get pushed away from it. Now, every piece of matter experiences a little bit of diamagnetism, but there's two other factors that play a role, paramagnetism and ferromagnetism, that are exactly opposed to this, and they're much bigger effects, and so they tend to dominate. Diamagnetism is very small, very weak, very hard to measure, and so we often don't measure it, except in a laboratory setting. It's not something you would normally worry about. Paramagnetism and ferromagnetism, those are big effects, and so that'll be our next topic.